Alrighty, so we're going to go ahead and jump right into module number one. And feel free to, like I said, ask me any questions at any time. Let me know if you have any questions and jump in anytime, all right? So in module number one, we're going to talk about several different aspects of wireless fundamentals. We're going to describe wireless components and what the topologies look like. We're going to take a look at radio frequency principles and the mathematics that are involved in dealing with radio frequencies. We'll take a look at antenna characteristics, a very important concept when designing a wireless network. You need to really understand antenna theory and how to apply different antenna components to the infrastructure so that you can have the appropriate coverage. We'll even take a look at spread spectrum technology. I'll get into a lot of detail on different spread spectrum characteristics. DSSS, frequency hopping, spread spectrum, orthogonal frequency division multiplexing, OFDM, which is what we used in modern wireless networks today. We'll take a look at wireless media access. In other words, how do we bridge the wireless LAN to the infrastructure, to the wired infrastructure. And then we'll also take a look at wireless governance. Not so much something that we care too much about. We don't really have a whole lot of say necessarily on how wireless is governed in the United States. It's, there are basic rules that you have to follow, and that's it. But it is good to kind of know what those rules are and what are some of the limitations that you have when implementing wireless over these, what we call these ISM bands, these industrial, scientific, and medical bands. So the wireless technology, and this is one of the fastest growing spaces there is in networking today. Wireless has always been in the past thought of as kind of like a basic add-on to the network. It hasn't really been considered as really a core component of communication on the network. It was more of a convenience, right? You had some devices or some users that needed to be mobile, so you added a wireless network. But now it's becoming more and more so that wireless is becoming the predominant standard for connectivity in the infrastructure. So we have to take into consideration cabling, we have to take into consideration security, and so on. So it is really an extension of the LAN. It's always kind of been an extension of the LAN, but now it's really becoming kind of the primary component because wireless speeds are surpassing what we would typically see in a wired network. Now, there are some limitations, and we'll talk about what those limitations are with regard to how clients communicate over that wireless network. The idea, though, and the thing that makes wireless so prevalent today is a lot of BYOD, bring in your own device, a lot of mobility, the ability to move from building to building or office to office and so on. So it's wireless is becoming more and more of a key component to the overall concept, right, of communicating in networks today. So we will talk about that, but before we get into the specifics of how Cisco handles wireless and what components we deal with in the Cisco world, what is clean air and what is radio frequency management and so on, and how do the wireless controllers work, I want to talk about some of the fundamental components of wireless. We'll look at some wireless topologies, like what is a WPAN versus a WLAN versus a WMAN. There's kind of some bleed over between those concepts there. We'll take a look at what an ad hoc wireless network is and what the limitation of an ad hoc wireless network is. What is Wi-Fi Direct, right? How do we use Wi-Fi Direct to connect wireless devices without the requirement for an actual access point? What is a Piconet? What is the purpose of a Piconet? Probably haven't heard that term or maybe not familiar with what that is right now. Bluetooth, right? And how does Bluetooth fit into this whole wireless network architecture? iBeacon, near field communication for radio frequency devices. ZigBee, we'll talk about different service areas, like a basic service area or a basic service set, extended service set, and so on. It's, you know, a lot of concepts that we kind of take for granted when we think about wireless, like a service set ID. But what is a BSSID? What is an MBSSID? How do we compare that and contrast that to what an actual SSID is? What is SSID cloaking, right? How do we hide our SSID? We'll talk about workgroup bridges and their unique deployment challenges that a workgroup bridge might solve, right? We don't see those too much in networks today, but there are some scenarios where a workgroup bridge would actually solve some basic connectivity needs that we have maybe in an outbuilding or some small office or remote office. We'll talk about repeaters and what a repeater does in a wireless network. We'll take a little bit of we'll talk a little bit about outdoor wireless. Not so much the mesh component, although we will talk a little bit about mesh. We're going to focus primarily on bridging, right? Bridging buildings between two locations with a wireless antennas and wireless components. We'll take a look at cordless phone technology. You might think, why would I do that? Well, because it can definitely affect your wireless environment. And then we'll also take a look at all those other what we call non-802.11 interferers, and how that can affect our environment as well. All right, so a lot of stuff we're going to cover in this environment, but I think in the initial part of this, you probably have a good understanding of what we're going to be talking about, but we'll get into some more advanced topics in this particular lesson as well. So I think you'll enjoy that. All right. So what is a wireless personal area network? We see these today all the time, right? We kind of take them for granted, but you know, everybody uses it today. When you're using Bluetooth in your car, when you're using Bluetooth wireless headphones with your laptop or whatever, it's just a wireless network that allows you to connect devices in a small area. Sorry, I had to cough there. That might be, you know, audio equipment in your media room, or it might be, like I said, in your car, Bluetooth equipment, wireless headphones, etc. A wireless LAN, of course, is a lot more robust. It's going to give you much more bandwidth. It's probably going to use some sort of non-proprietary communication protocol. Typically, it's going to be based on the 802.11 standard, right? IEEE standard for Wi-Fi networks. And that's obviously what we're going to be talking about in this particular class. A wireless MAN, what we call a metropolitan area network, just a wireless network that allows us to communicate over a larger geographical area. It says here anything above 100 meters. There's obviously typically a limitation of what that can include, but it could be point-to-point connections between buildings. We do that quite a bit with our customers, where we want to interconnect offices and we want those offices to be able to communicate with each other. So we're going to use wireless bridging to bridge those networks together, or those buildings together. Either in a point-to-multipoint environment where I have one access point that's providing connectivity to a whole bunch of different buildings, or point-to-point where we have a building-to-building communication. Is that something that you work on as well? Is that part of your infrastructure, Mike? I don't know if you heard me or not. Oh, sorry. Sorry about that.
That's all right. Ours are all through switches, so we have nothing that's communicating between buildings that isn't on the switch network.
Got it. Got it. Well, you'll find that the communication, the site-to-site communication with wireless is pretty prevalent today. It can be affected by weather, of course, weather conditions and obstructions between the buildings, but it's going to be limited a little bit in the amount of bandwidth that it's going to provide. But as the wireless technology continues to grow, you're going to see more and more high bandwidth applications available. There are, of course, licensed options that you have to be able to communicate between between buildings, but there, if you want to stick within the unlicensed bands, you have a little bit of a limitation on what you can actually do. But obviously, in order to be able to communicate with wireless devices, you have to have wireless capable endpoints, right? And over time, that's kind of changed quite a bit. In fact, in early days of wireless, when we were using things like just original 802.11, or we were looking at 802.11 standards, a lot of the hardware that was built was limited based on the security components that were integrated into that hardware. And so we saw when we transitioned from, say, like WEP over to WPA and then to WPA2, some of that hardware had to change. And we'll talk about that a little bit later on in more detail. Obviously, in order for us to be able to communicate over a wireless network, we have to have devices that communicate using the same technology. They have to understand and identify a group that they belong to. And when we have devices that are communicating without an infrastructure component, in other words, as the diagram shows here, we're communicating directly using essentially the wireless components in an ad hoc environment. This is what we refer to as an ad hoc network. One of the concepts is what we call a BSS, right? And you see that listed here on the slide as one of the components, IBSS, which is an independent basic service set. Basically, it means that it's independent of infrastructure, independent of a wireless infrastructure. A basic service set is essentially the area that a computer can be reached through its wireless connection. So we see three devices on this diagram and three blue circles. Those blue circles represent essentially their field of wireless connectivity. So the blue circle represents that basic service set. And we'll talk about different network or different infrastructures a little bit later. But essentially, that's the area in which that device can communicate wirelessly. We'll talk about signal strength and signal to noise ratios, and we'll talk about how those basic service sets are managed a little bit later on. But an independent basic service set, like I said, is essentially just a computer-to-computer wireless communication, which is what we call an ad hoc network. One of the technical limitations of this type of network is that you have to be in range of all of the other devices that you want to communicate with. In an infrastructure-based network, you can communicate to other devices over a wired network if you can't reach them from a wireless standpoint. But in this particular case, that's not an option. The other problem is that on the radio side of a wireless access point, that is half duplex. Now, we do have technology that simulates or at least facilitates quote-unquote quasi full duplex operation, right, with multiple input, multiple output technology. But traditionally on the wireless side, wireless communication has always been half duplex. It's we use a contention-based scheme to communicate over wireless called CSMA-CA. Now, I'm sure you've heard of CSMA-CD, which is carrier sense multiple access with collision detection. But in the wireless environment, we use something called CSMA-CA, carrier sense multiple access with collision avoidance. And we'll actually talk about that in more detail as we move through this particular lesson here. But it's a contention-based scheme that allows devices to identify when they're allowed to communicate over the wireless radio frequencies, so that we're not stepping on each other's toes, so that the devices are not interfering with each other. Another problem with this particular type of implementation is how do we group these guys together, right? If we have two ad hoc networks that are created in that same area, we have to be able to identify a way of differentiating the computers that belong to each network. And we can use work groups for that process, much like you would use a work group in a Windows environment to identify what clients belong with each other or what clients communicate with each other. We can do that in a wireless environment. Ad hoc networks are really not very popular today. They're kind of considered to be legacy, and a lot of OSs no longer even support the usability or the functionality of these ad hoc networks. But from time to time, you'll see a use for it. I can't recall the last time that I actually used an ad hoc wireless network. I suppose Wi-Fi Direct could be kind of considered ad hoc, like printing from your iPhone to your printer, directly without having to go through infrastructure. But it's kind of classified separately because of the security that's involved and so on. All right. So Wi-Fi Direct, which was actually called Wi-Fi P2P at one point when it was initially introduced, is a Wi-Fi standard that enables devices to easily connect with each other without requiring, again, a wireless access point. So it sounds very much like an ad hoc network, an IBSS, too many S's. All right. Essentially, Wi-Fi Direct allows two devices to establish a direct Wi-Fi connection. You don't need a wireless router. You don't need a wireless network. And we call this actually single radio hop communication because unlike a wireless ad hoc network or a mobile ad hoc network, Wi-Fi Direct doesn't use multiple radios to communicate. So that's we call that single hop radio communication. Conventional Wi-Fi networks obviously typically are based on the presence of a wireless controller, wireless access points, and the purpose of those devices is to provide basic functionality, right? Physical support for wireless and wired networking, so I can physically connect to some sort of SSID that's being broadcast, and then also connect to a back-end infrastructure, bridging and routing between devices on the network itself, and then service provisioning to add or remove devices to and from the network based on authentication events or whatnot. Additionally, in more advanced controller-based networks, we're also doing things like radio frequency management, radio resource management, and so on. Typically, when you have devices in the home, like a small office at home, or just regular devices that you're going to have at home, that's going to include, laptops or tablets or phones, even printers today, modern printers, all kinds of devices, right? We talk about the Internet of Things, and everything is now connected. Most Wi-Fi networks are going to be set up in this infrastructure mode, where you have an access point that acts as a central hub to which all of those Wi-Fi devices get connected. They don't actually communicate directly with each other. They go through the access point. Wi-Fi Direct devices are able to communicate with each other without requiring a dedicated access point. All right. There are some kind of new uses for this today. We see this with portable media players, phone features, being able to add Wi-Fi to smaller devices allows us to find printers or cameras or scanners without having to go through some sort of infrastructure. There is a technical component to this, of course. Wi-Fi Direct embeds what we call a software access point, or a soft AP, into the device that actually supports that direct communication. That soft AP provides what we call a version of Wi-Fi protected setup, and it has push button or pin-based access that allows you to access the Wi-Fi Direct. So when a device enters the range of a Wi-Fi Direct host, it can connect to it, gather the setup information using what we call a protected setup style transfer, and then the setup is kind of automated from that point. Soft APs can perform all kinds of different functions. We can use them for like digital picture frame, for example. In fact, I have one that I can push pictures to through Wi-Fi Direct. But that's only going to provide basic services, so I can push out video. You might also see the inclusion of security, right? WPA2, and so on. So a lot of uses for this. I'm sure you've seen this many, many times in your experience as well. Not something you're going to see too much in infrastructures, right? In businesses today. It's mostly going to be in the home. You'll see this kind of information. It is kind of identified as an IBSS, but it doesn't operate in IBSS mode, as I mentioned before. And the book states this, right? Wi-Fi Direct is an innovation that operates as an extension to an infrastructure mode of operation, all right? Which is what I had described previously. So it includes things like WPS and so on. Another type of wireless network is something called a Piconet. Again, probably something that you're not going to see too much in an enterprise network. But Piconets, well, it's another type of ad hoc network. It's going to link, as the diagram kind of describes here, a whole bunch of wireless users into a group, typically using some sort of Bluetooth technology, right? There's going to be 1 or 2 or 3 devices that have the same physical channel. And this is going to be synchronized to a common clock. So there's some timing that gets synchronized, a hopping sequence that we're going to use so we can manage the radio frequency. But what it does and how it's slightly different than what we saw on the previous slide, it allows a master device to interconnect up to 7 active slave devices. You can have other slave devices defined, right? In fact, up to 255 slave devices can be inactive. We call that parked, by the way. And then the master device can bring those devices into an active status at any time, but another active station has to go into a parked mode first. So we can only have up to 7 active slave devices. Some examples you might see, like cell phones connected to a computer or a laptop, maybe a Bluetooth enabled digital camera, PDAs, etc. Again, it's based primarily on the Bluetooth technology in an ad hoc environment. And it always starts with 2 connected devices and then grows up to 8 connected devices from that point. 1 master and 7 slaves. Okay. Let's see. I don't really mention too much else about that. Now, Bluetooth, of course, Bluetooth is a predominant standard that we see today in most networks or in most of our day-to-day operations, right? There's quite a bit that we could talk about with Bluetooth. I don't know how much in detail I want to get into this. I do feel like I should maybe get into a little bit more detail on this than I normally would. The book doesn't really have a whole lot of information about it. I mean, they do talk about the different classes and so on, so we'll get into that. But Bluetooth, again, another wireless technology standard. Generally, it's a wireless technology standard that allows us to communicate over very short distances. It actually uses short wavelength UHF radio waves. And you can see here on the slide in the band and the ISM band. Let's talk about that for a second real quick. ISM. ISM stands for the industrial, the scientific, and the medical. Industrial, scientific, and medical. We'll see this later in the slide deck, so I'm not going to pull up a graphic for it right now, but essentially ISM bands are bands that are used or regulated by the FCC or other regulatory bodies throughout the world, but they're open bands. You don't have to have a license to operate in these particular frequency ranges. 900 megahertz, 2.4 gigahertz, and 5 gigahertz are the three kind of general definitions of those three radio frequency spectrums or ranges. Now, that doesn't mean that it's the wild, wild west, and you can do whatever you want in these radio frequency bands, in these particular ISM bands. There are regulations that you have to follow, but you don't have to have a license to operate in these particular frequencies. The reason why this is particularly important, why we see the 2.402 and 2.480 gigahertz listed here, is because that happens to fall within the ISM bands, right? Like I said, there are essentially three different specifications for the industrial, scientific, and medical frequencies. And 2.4 gigahertz happens to be one of those. So we'll get into, when we get into the radio frequency spectrum and we start talking about the details of radio frequency, we'll talk about that in a little bit more detail. Why is it particularly important that we're concerned about Bluetooth in this case? Any ideas?
Interference?
Absolutely. Interference. Yep. There are, obviously we're going to talk about towards the end of this lesson, non-802.11 interferers. Well, Bluetooth falls within that category because it's not an 802.11 standard, but it does fall within that frequency range. Incidentally, there are several different frequencies that are allocated for different purposes, but the ISM bands are, well, we'll see what the specific frequency ranges are a little bit later on. But Bluetooth falls within that. Microwaves will fall within that, so they're going to cause some interference. And then we have 802.11 interferers, like co-channel interference and whatnot. We'll get into all that a little bit later on. But Bluetooth as a technology operates from 2.4 gigahertz to 2.485 gigahertz. It's obviously a technology that allows us to build those PANs. Was actually invented by a Dutch engineer. I can't think of his name, but he worked for Ericsson in the mid-90s. And it was actually developed as a technology to replace RS-232 data cables, so DB9, DB25 communication. Obviously, it's changed quite a bit over the years and has become much, much more of a predominant standard that we see today with any kind of personal area kind of communication. The group that manages this is called the SIG group, or what we call the Bluetooth Special Interest Group. And there is an IEEE standard as well for Bluetooth. It's 802.15.1. But IEEE doesn't really maintain the standard anymore. So Bluetooth SIG oversees the development of the specification, manages the qualification programs that are involved in qualifying devices, and protects all the trademarks and the patents and whatnot. All right. The Bluetooth is, like I said, operates in a frequency range between 2402 and 2480 megahertz. And there are some guard bands as well, what we call these 2 megahertz wide bands at the bottom and end of the 3.5 megahertz. There's a 2 megahertz wide guard band at the bottom of Bluetooth. There's a 3.5 megahertz wide band at the top. That's why the numbers will kind of change depending on who you ask, what frequencies are used. But it's an unlicensed band. Again, like I said, unlicensed does not mean unregulated in the industrial, scientific, and medical spectrum. The 2.4 gigahertz short range radio frequency band, to be specific. The radio frequency technology that's used is called frequency hopping spread spectrum. We'll talk about different frequency hopping methods later on. But what how Bluetooth essentially operates. There aren't any line of sight restrictions, as you see here. We'll talk about the different classes of products a little bit later on, but from a technical standpoint, Bluetooth divides the transmitted data, wherever it's coming from, into packets, and then it transmits each packet on one of the 79 different designated Bluetooth channels. There are actually 79 different channels defined within the specification. Each channel is very narrow, unlike like 802.11 specifications where I have 20 megahertz wide or 22 megahertz wide channels. In Bluetooth, we're only using a single 1 megahertz wide channel. We'll be hopping around using an adaptive frequency hopping method about 800 hops per second within that 1 megahertz wide band. Again, not so important for Bluetooth, but we'll get into the details of frequency hopping and why frequency hopping is so important in wireless communication as part of the process. All right. Now, there are a couple of different classes of Bluetooth as well. You can see that kind of listed here. When somebody says that a product has Bluetooth, they're obviously talking about something that has a Bluetooth radio built into it, which allows them to communicate in this 2.4 gigahertz spectrum, which is also, like I said, used in Wi-Fi. Specifically 802.11g as well as 802.11n. We actually use two different radio frequencies in 802.11n. There are 3 classes of power, and this is something that you would, I guess, be tested on if you were going to take the test, so it's something kind of important to know. But there's a class 1 device that has a maximum power of 100 milliwatts and a range of about 100 meters. Okay, so almost like an Ethernet cable, basically. But obviously, in order to be able to support this class, you would have to have, a significant battery, or you'd have to have a significant power source to be able to support this because of the power consumption that's required. So you don't see class 1 devices in like your mobile phone or your head, your earphones or whatnot. Class 2, 2.5 milliwatts, a range of about 10 meters, and then class 3 devices, a 1 milliwatt with a range of about 1 meter. Obviously, you can understand the different applications here. If I've got wireless headphones that are connected to my iPhone, I don't need to necessarily have a class 3 device, right? Obviously, there's different applications for different types of Bluetooth. Not only are there different classes of Bluetooth, but there's actually different specifications for Bluetooth and different features for Bluetooth as well. Remember, the SIG, that's Special Interest Group, was formed in 1998, so it's been around for quite some time. But there are many different kind of variations and versions of Bluetooth. You started with Bluetooth 1.0, and then you went to Bluetooth 1.1. I don't want to get into all the specifics of what changed between them, but now we're all the way up to essentially Bluetooth 5, right? 5 is the latest version. It came out in 2016. Mainly focused on this whole concept of the Internet of Things. Samsung Galaxy S8 supports Bluetooth 5, iPhone 8, 8 Plus, iPhone 10, they also have Bluetooth 5 support. And again, without getting into the specifics of what it includes, because it's not really necessary for this particular class, it has long-range capabilities, higher output powers, park states, and so on. We don't have to get into the details of that. Certainly, if you want to learn more about the different versions of Bluetooth, you can look into that. But for the most part, we don't really concern ourselves with that too much in this class. Okay. Like I said, several generations. When this book was published, Obviously, Bluetooth 5 had not come out, so that's why I mentioned that. Obviously, Bluetooth devices connect with other devices. We create this kind of master-slave relationship. And we can talk a little bit about the pairing mechanism. Pairing mechanisms have changed over the time since introducing Bluetooth originally. You have kind of a legacy pairing method, which was only available in Bluetooth version 2, where you would actually have to enter a PIN code, and pairing would only be successful if both devices entered the same PIN code. And we would use any 16-byte string as that PIN code. The problem is that you might have devices that don't actually support that functionality. Now we have kind of what we call this SSP pairing, which is, I'm trying to think of what it stands for now, it just escaped me. Secure Simple Pairing. Anything Bluetooth 2.1 and above is going to support this. We use actually PKI, public key cryptography, to pair. That's going to protect against man-in-the-middle attacks, and it has a couple of different authentication mechanisms. There's passkey entry, there's out-of-band management, numeric comparison, and so on. Obviously, the whole idea here is that we're introducing additional security and trying to protect against what we call bluejacking and other types of security concerns that might be introduced with Bluetooth. Incidentally, I'll just mention it. Bluejacking is kind of spamming Bluetooth devices through their wireless communication. It's more of a script kiddie type thing. I mean, it's not really I haven't seen it as a predominant hacking method, although it is a concern, right? I mean, you think about all the devices that are connected with Bluetooth today, especially vehicles, right? Vehicles communicate with Bluetooth. There is a concern that somebody can gain access to the computing systems in that vehicle based on that. But again, not part of this particular class. Okay. Bluetooth Low Energy. Version 4 of Bluetooth came out with this thing called Bluetooth Low Energy, or Bluetooth Smart. It allowed devices to communicate, like I said, with other devices. 20 dBm. We'll talk about dBms and dBis and dBs later on and what the difference is between them. dBm is a decibel in reference to a milliwatt, but that's going to provide up to 100 meters of communication at a lower power, so we can get that communication. Remember, if I wanted to do 100 meters of communication previously, I'd have to have a class 1 device, which took a lot of power. Okay. All right. Incidentally, we will be taking a break. Not now, but we'll take a break maybe when we finish this particular lesson here. All right. All right. Another technology actually developed by Apple, fairly new, introduced in 2013, is a protocol developed by Apple called iBeacon. Apple's not the only vendor that's making devices that are iBeacon compatible. Typically, we call these beacons. It is a version of BLE, right? This Bluetooth Low Energy that broadcasts an identifier to other portable electronic devices. This is going to enable things like smartphones and tablets to perform kind of an action when they're within close proximity to an iBeacon device. So it transmits, since it's based on the Bluetooth Low Energy proximity sensing component, it transmits something called a universally unique identifier. We see these all the time in computing today, where devices are identified by these UUIs. And that would be then picked up by a compatible app or some sort of operating system and so on. The I'm trying to think of an example of where you see this today. Yeah, I'm trying to think of one. I mean, I know that it is part of lots and lots of devices today. Anything that supports Bluetooth 4 and above, which has been around for a while, right? iPhone 4S supported Bluetooth 4 and above, iPad first generation, and so on. It's another way of communicating, and provides that that communication. I don't know. I don't think we need to get into it in a whole lot of detail. It's just the whole point of this discussion is really to just give you an idea that 802.11 is not the only wireless that we need to concern ourselves with, right? There's other types of wireless technologies that exist. But the key is that this exists in the same spectrum and the same space that we're having to manage our wireless networks in. It's very interesting. If you install a clean air access point, you're doing some sort of clean air inspection using the tools that we'll talk about later, you can actually identify or see when Bluetooth devices are enabled and see the interference that they're creating in the network. And there's a lot of ways of managing that. So we'll talk about that a little bit later on. Near field communication. As it describes, the range is 10 centimeters. Right? So we gotta think, well, why would I want that? Well, there's a lot of reasons why you would want to communicate wirelessly within that proximity. I'll talk about some of the applications of this a little bit later on. But basically, what near field communication is just a set of communication protocols, essentially allowing two electronic devices, one typically a smartphone or some sort of mobile device, to establish communication by bringing them typically within 4 centimeters of each other. I know it says that there's a 10 centimeter limitation, but it's typically about 4 centimeters. The most common application of this today is contactless payment systems, right? When you tap your phone or you tap a credit card to a payment terminal, that is near field communication. Electronic ticket smart cards, mobile payment, that kind of thing. It can be used for things like social networking, sharing phone contact or photos and whatnot. You know, when you can put two phones together and wirelessly share contacts or photos or videos, that kind of thing. Can also be used for things for security, right? Electronic identity documents, key cards, and so on. Very, very low speed connection. Simple setup, very, very basic. All right. Similar ideas were developed for obviously industrial applications, not really successfully commercially. Obviously, there's a big limitation to the distance with near field communication, so we don't see this too much commercially, but that's the basic concept. We can use smart tags. The tags are basically just RF stickers that you can put on a device. They can hold maybe half a byte or 4,000 bits or bytes of data, and they can be read only, read write, etc. We can use this for RF tagging or RFIDs and so on. So again, another concept of wireless. Although we don't really concern ourselves too much with this one because of the distance limitation, it doesn't typically affect our enterprise wireless network. Another type of wireless technology is what we call ZigBee wireless. We see this a lot in thermostats. I've got an Ecobee thermostat at home, and it's got a bunch of these little sensors that you can put around the house. So not only am I measuring the temperature of the house at the thermostat, I've got 6 or 8 or 10 different sensors placed throughout the property that report back to the thermostat on the temperature of the whole room, right? So I've got one in the bedroom, I've got one in the garage, I've got one in the living room. So I'm getting a much more accurate representation of what the overall temperature is of the facility, rather than just looking at what it is at the thermostat. All right. This is an IEEE standard. Excuse me, I didn't mean to cough in your ear there. This is an IEEE standard, 802.15.4. It's got a bunch of high-level communication protocols to create essentially this personal area network. But the key with this is it's low power, right? The digital radios, like I said, used primarily for home automation. You can see this for medical device data collection or anything that requires low bandwidth. But the low power is the key here, because that's always been a critical component to dealing with things like Bluetooth and other wireless technologies, is how much power consumption am I going to be required to have. In this particular case, very, very low power, but also low data rate, and you have to have close proximity. It is a wireless ad hoc network, and obviously the whole goal here is that it's simple, less expensive than implementing other WPAN options like Bluetooth or even Wi-Fi, for example, ad hoc Wi-Fi. Light switches, home energy monitors, traffic management systems, all kinds of things use this technology today. It can transmit anywhere from 10 to 100 meters line of sight, depending on the power output, environmental characteristics, etc. They can transmit data over a much larger network or a much larger distance, but you would have to relay that information through some sort of external network like a mesh network and so on. So ZigBee devices, they're typically going to be used in low data rate applications. You need a long battery life. You need secure communication. You can see here that it's very secure, uses AES, Advanced Encryption Standard 128, available, self-configuring, and so on. This has been around for a while. It was the idea was conceived in the late 90s, but it was actually revised or ratified as a standard in 2003. Yeah, it's an interesting concept. You would see, you'd be surprised how many devices are actually utilizing this this technology today. Let's see. Again, just to introduce the concept, not really, we don't need to get into the details of, you know, what types of devices there are. I mean, there's all kinds of devices that actually perform functions within a ZigBee model. You've got a ZigBee coordinator, you've got a ZigBee router, a ZigBee end device. These are definitions that define different types of devices. Those are the three, anyway. I don't know that we need to get into the details there, but we can certainly take a look at that later if we have some time. I doubt we will, but all right. Now, there is a slide here that kind of describes the process of how devices communicate. So I guess we will go into it a little bit here. The ZigBee coordinator is kind of the root of the network tree. And it's actually, the purpose of the ZigBee coordinator is to bridge other devices. There's only one ZigBee coordinator in each network, since it is the device that started the network originally. It uses something called the ZigBee Light Link specification. I think that's what it's called. Essentially what the ZigBee coordinator does is it stores information about the network that's being constructed, and it also acts as the trust center and the repository for all of the security keys that are going to be used in the environment. You have another component called the ZigBee router. Obviously, it's going to be running the ZigBee application, but it can also act as an intermediate router, passing data from one device to the other device. So some of these dots on here, these blue dots on here that you see here could be acting as not only as a ZigBee device, but or an end device, but actually as a router as well. A ZigBee end device, which is really what we see with the red circles here on the diagram, they're going to contain just enough functionality to talk to the parent node, whether it's a coordinator or a router. So you're only going to have one coordinator in the entire infrastructure. So on this right diagram here, maybe this particular device is the coordinator. These would be classified as routers in that case, and these would be our ZigBee end devices. The ZigBee end device has limited functionality. That means it cannot relay data from other devices. The ZigBee end device can be asleep. It can be transmitting data. It doesn't have to be active the whole time because it's not acting as a coordinator and it's not acting as a router. The idea is that if I'm not transmitting or I'm not receiving data, I can go to sleep, preserve the battery life. It's going to require the least amount of memory and so on. All right. Now there are a couple of different communication models with these devices. There's some discovery models. I don't think we need to get into all the details of that. There are network layer components to this, application layer components, but let me just talk about in a little bit more detail the ZigBee protocol stack, because I think that's interesting in this concept here of how ZigBee works. The ZigBee device object, or what we call the ZDO, is a protocol in the protocol stack. And the whole function of the ZDO is device management. That includes policies, security keys, and so on. It's responsible for defining the role of a device, whether it's an end device, a coordinator device, a router, as we mentioned before. But it's also responsible for discovering new devices on the network, identification of what services that device can provide or what services or functions that device can provide. And then it establishes the secure links between those devices and other devices. Again, we don't need to get into the specifics, I guess. It is an interesting protocol, very prevalent today. It can operate within the same frequencies of Wi-Fi, but it's not a Wi-Fi device, meaning that it's not an 802.11 specification. So this again will be classified as an 802.11, a non-802.11 interferer. So a ZigBee network can't communicate directly to an 802.11 wireless network, obviously. The maximum power of a ZigBee device is 60 milliwatts, which is pretty significant if you think about it, because on a wireless network, the maximum transmission power is 100 milliwatts. So these ZigBee devices can operate in a pretty significant power spectrum that could interfere with our 802.11 wireless network. All right. We don't typically see powers that high, but we can see that if in certain scenarios. Okay. In infrastructure mode, essentially infrastructure mode basically just means that we have wireless access points that are connected to our infrastructure. So we have communication that can occur between devices connected to the wireless access point, but they can also communicate to devices that are connected to the LAN, right? Now we see what we call a BSA. A BSA stands for our basic service area. And that's the wireless cell that wireless access point is providing services for. And the size of that BSA is going to depend, of course, on the types of antennas that you're using. The shape of that BSA is going to be dependent upon that. How much transmit power you're using, other types of factors. And we'll talk all about how to manage these basic service areas. The central device is the access point. The access point is essentially a hub relaying wireless communication, but not ad hoc, right? The devices are not communicating directly with each other. They're communicating through the access point. Although it's a little bit more complex than peer-to-peer, it's typically a lot better because we have more security, we have better management of the congestion in the network, and then also we have the ability to communicate to our distribution system, which is our LAN. So obviously that's going to provide a benefit over some sort of ad hoc network. The comparison to a hub is made because of the half duplex nature of the wireless side of the radio. Again, we have technology today that can manage that process and make it appear as though it's full duplex, but traditionally the radio side of any wireless communication has always been half duplex using that CSMA CA method. And we'll talk about the CA, the collision avoidance techniques that we use, like CTS and RTS and so on. Also, APs have a lot more functionality that wired networks don't. They can direct Wi-Fi traffic. They can apply quality of service. They can manage MAC address tables. They can direct packets to particular ports because it is a bridge. I mean, it is essentially a device that understands layer 2 communication. And of course, we can apply security based on that as well. We can do MAC filtering, and we can apply different security filtering techniques based on the ability of understanding layer 2 header information. An 802.11 header typically has 3 MAC addresses, but it can have up to 4. And let me see if I can pull up. Well, I'll do that a little bit later on. I'll show you guys, Mike, sorry, what an 802.11 header looks like. But it's pretty complex. There's quite a few things. I mean, it has the basic concepts: header, data, footer, frame check sequence, and so on. But you might consider, why do I have to have so many MAC addresses? Well, you've got a MAC address for the radio. You've got a MAC address for the client that's actually sending the data. You've got MAC addresses for the distribution system, plus you have MAC addresses for the actual endpoint. Now it says here that we typically will communicate using 3 different MAC addresses. Those 3 MAC addresses are the sending and receiving client, the BSSID, the basic service set ID, the SSID that has a MAC address tied to it, which is the radio side, and then you have the MAC address of the destination. Later on, we'll talk more about layer 2 addressing schemes and how wireless frames are forwarded to the upper layer and so on. Wireless capable devices are called stations. End devices are often called client stations. And then the AP is referred to as our infrastructure device. Like a PC in an ad hoc network, the AP offers a basic service set. When you have multiple basic service sets, we call this an extended service set. Now, an AP does not create what we call the independent basic service set. Remember, that means that we're doing ad hoc wireless, which would not include an AP at all. The area that the AP radio covers, the coverage area that the AP provides, is called my basic service area or my radio cell. Because client stations connect to the central device, this is what we call infrastructure mode. And what they mean by this is that we're not just communicating from one wireless client to another, we're communicating to our distribution system and we're communicating to devices in the infrastructure. Now you'll notice in this particular diagram, you see 2 different APs offering 2 different basic service areas with some overlap. The amount of overlap that you need to have between the cells will depend on what you're implementing in the network. If it's voice, you need 20 to 25% overlap. If it's just data, maybe about 10 to 15% overlap. But then you also have to concern yourself with what we call co-channel interference. I don't want to get into it in too much detail right now. We'll talk about the radio frequency spectrum and 802.11 and how the channels are allocated and whatnot. But in this particular case, channel 1, channel 6, they do not interfere with each other because they're in completely different spectrums. So we do see those channels used typically quite a bit in 802.11b and 802.11g implementations. When the distribution system links the two APs, this is called an extended service set, meaning that I can move from one basic service area to another, assuming that I've designed the network correctly and I have the appropriate signal properties, RSSI and signal to noise ratios and whatnot. And obviously this is what we typically do, right? That permits roaming between the network. A roaming is essentially occurs when a station leaves one coverage area of an AP that it was originally connected to, and then it moves to another AP. There are two things that will allow a client to determine whether or not it should roam. I'm going to unmute you here. What do you think those two things are? There are two measurements that a client will look at to identify when a roaming event needs to occur. Any ideas?
Signal strength?
Yep, RSSI, yep. And? Any ideas?
Proximity? I don't know.
SNR, signal to noise ratio. So that is a concept that's very important to understand in wireless. Obviously, the analogy that I use is when I'm teaching in a classroom is if I've got 20 students in the classroom and I'm the only one speaking, very, very low signal to noise ratio. My signal is very high, the noise is very low. So signal strength is not the only thing that we need to consider when we're considering how we're communicating over wireless. I could be sitting right next to you communicating, but if there are 20 other people in the room screaming at the top of their lungs, it might be very difficult for you to hear me even though you have a high signal strength because the signal to noise ratio is so poor, right? There's a lot of noise. So signal might be 20, let's just say, noise might be 10. So that's a ratio of, a 5, all right? But if it's 20 to 1, that's a much better ratio. So we always consider signal to noise ratio as well. And noise is caused by other APs maybe operating in the same frequency or even, non-Wi-Fi interferers and so on. Of course, the goal is to make sure that we have seamless movement from one AP to the other. Now that's managed quite easily today because of the converged access and centralized management of the controller, where we don't even have to re-authenticate, but or lose connectivity. But obviously, design is a very important concept to that. We do have overlap between the cells. Obviously, it's important because that overlap occurs, and you have to have that overlap, that the APs are not operating in the same frequency, the same channel. Otherwise, you're going to get a lot of noise. And then we can get what we call co-channel interference, which then effectively hinders your communication capabilities. The wonderful thing about centrally, I lost my train of thought there for a second. Centrally managed environment is that we have something called RRM, Radio Resource Management, where all the APs are talking to each other. They're all identifying, their BSA characteristics, and the controller actually reprograms the APs, turns up the transmit power, turns down the transmit power, changes channels, changes frequencies, and manages that whole domain so that you don't have to worry about doing any of that. And that's something that we'll talk about when we get into the configuration a little bit later on. Another concept, of course, something you're probably familiar with, is something called a service set ID. In order to roam from one AP to the other, the APs have to share the same network name. Well, that network name is called the SSID. or service set ID. It's a just an ASCII value up to 32 characters that identifies the wireless network. And then obviously there's authentication that's involved with connecting to an SSID unless it's open. But in order for me to move from one network to another, I have to have a common SSID. So let's walk through the scenario here. You can kind of see on the diagram here, I'm moving from the BSA and channel 1, and that access point is advertising two different SSIDs, guest and voice. The SSID is actually the name, but you'll notice that there is something called an MBSSID. All right, and MBSSID allows us to identify essentially the MAC address that's used for that communication process. That's the MAC address to SSID association. So you'll notice that you actually have separate MAC addresses for each SSID, even though it's using the same radio, the same access point, you have a separate MAC address. That's why we said when we're identifying an 802.11 frame, there's often 3 different MAC addresses in that process. So when you have a profile that's configured on a client station, you just simply configure the SSID name that identifies the wireless LAN that the client wants to connect to. The AP associates the MAC address to that SSID, and then that MAC address can be the MAC address of the actual physical radio. Typically it's not. Cisco APs, we generate a separate MAC address for each SSID, but there are some vendors that can only support one SSID, so that means that they're just going to go ahead and use the MAC address of the radio. In the case of Cisco, like I said, we support multiple SSIDs. Because each AP has a different radio MAC address, the derived MAC address is different on each AP for the same SSID name. So we see that here on the guest on the left, you have 7804, but on the guest SSID on the right access point, Echo Foxtrot 35. This is actually very useful because it allows us to easily identify where frames are supposed to be forwarded and who's actually managing those frames. The name of the MAC address that is associated to an SSID is called the Basic Service Set Identifier. We see that on the right side, right, where you see the underline under 00112F06EF36, that's the Basic Service Set Identifier. And then on the left, the name, the ASCII name, is just simply the SSID. The whole point is that the Basic Service Set ID identifies the basic service set that is determined by the AP's coverage area. You know, terms that we looked at previously when we were looking at just a single AP and a single BSA. We don't really call it a BSA if there's only one AP. We just call it a basic service set. But because this is an extended service set, not just a basic service set, so we're throwing out a lot of terms here, so let me go back and explain. A basic service set is just simply a single AP connected to an infrastructure, no other APs in the enterprise. An extended service set is multiple APs with multiple BSAs. So it gets a little confusing because a basic service set also has a BSA, but the BSA is the basic service set, if that makes sense. In this case, we have an extended service set, which means we have multiple BSAs for coverage. So, you know, terminology, I guess, is the key here. I mean, this is not something new to you. I know you've dealt with this before and you know understand these concepts. But obviously, if you do decide to go on and take the exam in the future, you need to know all these terms. All right. An MBSSID is basically just a virtual access point. Remember, we're tying that MAC address to that SSID. The other option that you may choose to do or not do is whether you advertise an SSID or broadcast an SSID within the beacon. There are these things called beacons that get sent out that allow us to identify the properties of a wireless network. And typically within that beacon, within this information that's being broadcast, the SSID is advertised. A hidden network is not undetectable, right? SSIDs are advertised within the Wi-Fi packet, but you can still identify that these networks exist because there is a physical layer transmission that's occurring. So you can use a spectrum analyzer or some other types of tools to identify that the network exists. But you can also further obfuscate or hide your network by not advertising your SSID if you choose. All right. Another concept in wireless technology is a workgroup bridge. You might run into a situation where you have some wired clients connected to a physical device, like a workgroup bridge, which is a wireless device, but it's configured to operate a little bit differently in that it's bridging traffic from a local area network over to an access point. Hold on one second. Sorry about that. This is not used too often. I mean, I don't really need to get into the details of what this does. Obviously, it's you can kind of visualize or, oops. Obviously, you can kind of visualize or identify what the purpose of a workgroup bridge is here. We used to use this quite a bit back in the day when you wanted to extend your wired network to an outbuilding or something like that, but you didn't really have any physical cable plant to that outbuilding, so you would just install an access point, which is operating as a client-based access point, but it can transmit and receive data to a workgroup bridge. Cisco provides two forms of WGBs, the standard one, which is a Cisco one or a universal one. Basically, it just allows multiple Ethernet clients to communicate to an upstream AP. And it uses a proprietary protocol so that so the workgroup bridge can only communicate with the AP, or with a Cisco AP, I should say. That's the Cisco version, the standard version. I think we actually get into a little bit more detail on this later on, maybe identifying kind of how we can implement this a little bit later on. But again, like I said, it's not really something that we see too often today. Repeaters as well. An extended service set connects different APs together. But if you have a very large area like a warehouse, putting a cable into the middle of that open space might not be really possible or very practical. You can only go up to 100 meters or 328 feet with a twisted pair Ethernet cable. So you might want to extend your wireless network to include that particular area. It's different than a workgroup bridge. Because in a workgroup bridge scenario, we're trying to connect wired devices or extending our network to wired devices. But in a repeater mode, we're actually just extending the wireless signal to other wireless devices that are not in the range. So that's what a repeater does. Keep in mind that when you're operating in repeater mode, that you are operating with half duplex communication. So the signaling or the communication that occurs between the devices in this environment could be, slow or not really as high performance as you would see in a standard client to client wireless network. The other thing that you notice here is that the required overlap is 50%. That's significantly higher than what you would typically see with, if you're running an extended service set with multiple BSAs, and so on. Another concept, outdoor bridging, of course. We talked a little bit about this earlier, whether it's point-to-point or point-to-multipoint, allows us to communicate between facilities using our ISM bands. Really no different than really a standard access point. The only difference might be that we've provisioned the APs with directional antennas like a Yagi antenna or a patch antenna, or a parabolic dish, or obviously we're going to be transmitting at a much larger, over a longer distance as well. We'll talk about antenna theory and how we can manage that a little bit later on as well. All right. Now, a mesh network, a little bit different, obviously. In the case of a mesh network, the goal in a mesh network is to create not only communication between two different distribution systems, so a distribution system on the left and a distribution system on the right, but also to allow for connectivity for devices in between. They're missing an access point on here, but there's supposed to be one in that little circle right here, obviously. But the whole point of a mesh network is to provide kind of this mesh of coverage over a large geographical area. The mesh nodes act as repeaters, so they transmit data from nearby nodes to peers that are too far away from the distribution system. But they also allow for connectivity locally, right, for clients in that space. We see this a lot in metropolitan area networks and so on. You know, cities and parks and whatnot. Excuse me, give me one sec. Sorry about that. I had to get a drink of water. In a typical mesh deployment, dual radio APs dedicate a radio for the backhaul to reach the wired network. And then they dedicate a radio for clients themselves. Like I said, we're providing two services in this particular case. The AP node that has the connection to the wired network is called the RAP. And the nodes that are non-wired are called the MAPs. So the root AP is what goes back to the distribution system, and the mesh AP is what is connected to infrastructure. The clients and whatnot. And then Cisco uses an algorithm called AWPP. We'll talk about that a little bit later on, although this class doesn't really get into mesh technology too much, that allows all the kind of the routing over this mesh network to occur. Identifying the shortest path and so on. Now, the last thing we'll talk about in this section here. Now, we mentioned cordless phones in this case. And the reason we mentioned cordless phones is because of the frequencies that they operate in. 900 megahertz, which happens to be the first band within the ISM spectrum. 1800 to 1900 megahertz, which doesn't really affect us too much. But then we get to 2.4 gigahertz phones and the 5 gigahertz phones. Well, obviously, those phones are going to cause some issues in our wireless spectrum, especially because these phones tend to operate at higher power than your wireless access points. You know, anything that's a wireless access point, the effective isotropic radio power from an AP is about 100 milliwatts, or can be up to 100 milliwatts based on regulation. While phones can operate even higher in a higher power range than that. Most US phones use digital enhanced cordless communication, what we call DECT, or a variant, that is, it's not 802.11 communication, but it does operate within the same frequency as our 802.11 wireless network. So it is a big concern. We don't really need to get into the protocol itself. Wi-Fi 802.11 and DECT are not compatible with each other, but it does cause interference, particularly in 802.11b. Now, most phones today are not really, they don't really operate in that 2.4 gigahertz range, but it can have a huge effect because, again, even though you think of a cordless phone as kind of a benign type of device, it can operate in up to 250 milliwatts in Europe and up to 100 milliwatts in the United States. So obviously, given that our wireless access points can only operate up to 100 milliwatts, that can be pretty significant. We'll actually see later on how we can identify those decked phones and identify and troubleshoot our environment to identify that. Mostly the controller handles that process with radio resource management and manages that process. But in 802.11a, of course, we can also see interference. 802.11a operates in the 5 gigahertz spectrum. So obviously a 5 gigahertz cordless phone is going to have an effect on that. When you look at 802.11n, which operates in both the 2.4 gigahertz spectrum and the 5 gigahertz spectrum, obviously these cordless phones would affect that as well. There are other non-802.11 interferers that exist. Believe it or not, a microwave. It's interesting because I ran into a scenario recently where I was teaching a class, and it was at a customer's facility, and I kept losing my connectivity to the network. But it was very, very specific. It would happen over maybe a 1 minute or 2 minute period, and it really got bad during lunchtime. Well, turns out that the conference room that I was teaching in was right next door to the break room that had a microwave. And sure enough, whenever somebody was using the microwave, it caused a lot of interference. They're high duty cycles, high power. You know, microwaves obviously operate at a very high power level, but microwaves don't contain all of those microwaves. They actually will, about 100 milliwatts or maybe a little bit more than 100 milliwatts of interference will actually escape that microwave. So it can actually be pretty significant as well. Anything that operates in these frequency ranges that uses, doesn't have to be an 802.11 device, right? It just has to be anything that operates in that frequency range. So it can be a light bulb, wireless cameras, motion detectors, game consoles, whatever. So we use, in the Cisco space, we use something called clean air access points. And the clean air technology uses something called Spectrum Expert, which allows us to identify interference in the radio frequency spectrum. And we can take action based on that interference, switch to a different channel, identify different ways of managing that interference. Very, very smart technology. We'll get into that discussion a little bit later on. Okay, so that finishes up our first very, very basic lesson. I promise the next few lessons will get more technical, but we talked about, essentially the different terminology that we use to identify different types of networks: a basic service set, an extended service set, a BSA, a basic service area, the distribution system, and so on. We talked about Adhoc Network, Wi-Fi Direct, we talked about a lot of other different wireless technologies like Piconet and ZigBee wireless and Bluetooth, and how SSIDs work and so on. In our next lesson, we're going to get into actually some pretty good stuff. We're going to talk about radio frequency principles and talk about the RF spectrum and how wireless communication occurs and so on. So that'll be a really good lesson.